Hello and welcome back to another LeetCode problem. So this one is a medium problem which I really liked. So I wanted to show you how you can solve that. So this is LeetCode 173, binary search tree iterator. We're supposed to implement a BST iterator class that represents an iterator over the in-order traversal of a binary search tree. So it has a constructor to initialize the iterator with the root of a binary search tree, and the pointer should be initialized to a non-existent number smaller than any element in the binary search tree. Okay. Has next should return true if there exists a number in the traversal to the right of the pointer, otherwise return false. Okay. Next moves the pointer to the right, then returns a number at the pointer. Notice that by initializing the pointer to a non-existent smaller number, the first call to next will return the smallest element in the binary search tree. You may assume that next calls will always be valid. That is, there will be at least a next number in the in-order traversal when next is called. Interesting. Number of nodes is constrained. The values of the nodes between 0 and 10 to the 6. And we'll have at most 10 to the 5 calls to next and has next. And there's a follow-up as well. Could you implement next and has to run an average for O of 1 time and use O of h memory, where h is the height of the tree? Okay, so this is an interesting problem because normally when you do like in a traversal of a tree, you do the whole traversal in one shot, right? You don't stop. But here we need to stop the traversal and then continue when we call next. So that is an interesting problem, I think. So let's look at an example here. So we are calling the constructor, and then we call next, next, has next. So the output should be constructor calls null. So next, next. So it returns the 3, the 7, and has next is true because there are more. So when we call next again, it returns 9. Has next, yes, has another one. That returns true. Then we call next, it returns the 15. Then it calls has next again, which is true. Then it calls next, which is the 20. And then when we call has next the last time, there's nothing that comes after 20, so it returns false. Interesting. All right. Yeah, that is kind of a cool problem. So, well, if we think about how we would do a traversal when we do it in a one shot, you know, we would have some recursive call where we would say, if we do an in-order traversal, for example, wait, what kind of traversal is this? Search Tree Iterator is an in-order traversal. So in order would be 3, 7, 9, 15, 20. Yeah. So the in order returns the result in sorted order from the binary search tree. Okay, cool. So if we do an in-order traversal, normally what we would do is we would say visit left subtree, emit node value, visit right subtree, right? That's an in-order. If we change the order, then like so, that would be a pre-order traversal, and that would be a post-order traversal if you put it in the end. And I think all of these problems have this exact same solution. I think we can maintain the flexibility to change the order traversal by changing the order of these operations if we put them into our solution. So I think we'll have a linear time solution because we need to visit every node. And we're going to use an O of h space simply because we need to descend into the tree and know where we came from, right? A naive approach would be to compute the complete traversal first in one go, and then pretend that we are doing the traversal as we call next. So You know, we could do that. Should we do that? Why not? Let's just be dirty. Let's just do this. Def get traversal. So this is our little cheater method, and it will return us basically the result. Traversal, and we will have a simple in order traversal. We could do that recursively, right? So we have a node and we have a result to which we will append. And then we do this. If not node, return. That means we've reached a leaf. If node.left, we do helper node left.result. And otherwise, we're going to append the current node value to the result. Result.append node.val. And if node.right, so if we have a right child in the node, we go down that path after emitting our node value. Helper node.right result. Right, and return result. And yeah, so what we'll do is we just return helper self.root and our little result array. So that's how we can cheat. And a little bit. Self.root is root, and then with a self.result is self.cheat. Let's just call this cheat. Cheat. And we're going to call it on the node root. Call it root, so like so. And yes, and then we just need to maintain our little pointer. Or actually, what we could do is we could just reverse the list. Nice. And then when we call next, we just return self.result.pop. And otherwise, and then we just return if we call as next, we will just return the length of our result list is not 0, right? Yeah, and I think with that little dirty trick, it should work, but it's but of course that's not what the intention is of this solution. Wait, if not node, return result. Node is written in lowercase. There you go. Right, so that would work. Let's actually see if the solution gets accepted. Okay, yeah, well, but we cheated, right? So this is not really the problem that they asked us to solve, but we can use this idea of this traversal. So what we can do is if our next method advances our stepping through the pointer, all we need to do is we need to maintain a stack to know to what node to return after we've processed that node. And maybe if we're at this node 15, we want to put onto our stack the right subtree so that we process this later. We want to put our value on the stack so that we emit that value later, and then we put the left subtree on the stack so that we start to process that left subtree first, right? Because that's the order: left before emitting, before the right. So yeah, let's try that approach then. So self.stack is going to be well, an empty list, and we have to think about how are we going to differentiate between nodes and values to emit, right? And a simple way would be, well, we could always check if the element in there is a tree node object. We could do that, or we could just be a little bit more lazy and we just do like so. If we put an array of length 2 in there, and the first element is the node, and if the node is none, then the value is there's a value in the second one. So I think that would be easy enough. And yeah, and so now all we need to do, so if there's a next element, that means we still have elements on the stack. So there's this one. So we just do this. And we can, well, I'll leave the cheating method here, so just that we can reference it. Now, how do we implement the next? Well, next is kind of easy. So what we have to do is, well, sure, they could probably check this, even though the problem description doesn't tell us that we need. If self has next, Then we do some processing. Otherwise, we're just going to return maybe -1. Just for good measure. That's good coding style, even though the problem doesn't necessarily require it. But we know that all the values of the node are below, are larger or equal to 0. So if we emit -1, that's clearly an indicator that this is not a value that comes from the tree. So has next. Well, what do we do? Well, we pop the next node or the value from the stack, right? Self.stack.pop. So now if node is none, that means we have a value in here, right? That's what we decided. So we just return the value because we're emitting only the value. We don't have to do anything else. And yeah, but if it's not the case, well, in this case now we have to use our little logic here. So we have to do the following. We have to check if node.left, right? If there is a left child of the node, we have to, a right one, right? We have to put the right one first, then the value, and then the left. That ensures that on the stack, the left one is the top one, and because that needs to be processed next. So if node.right, in that case, we're going to say self.stack.append, and we're going to use our format from above again. Then that is node.right, but not a value. And for the left side, it's the same, self.stack.append, node.left, and no value. But here, we also need to put our current node's value so that we make sure that we emit it. So self.stack.append, and now the node is none, and we put the node value. So it's not this value, it's the node that is not none. Those values we put in here. And right, so, okay, cool. So now let's say we're just processing a root. So we put this element on the stack. We put the value 7 on the stack, and we put the node 3 on the stack. But we still have to return something, right? So we're not returning a value just now because we have a node. We have the root node. So what do we do? Well, so this is now the cool thing. So what you do is just you return self.next. So we continue processing the stack, meaning we're going to descend to the leaf node. In the leaf node, there's no right and no left subtree. So we place the value 3 on the stack, not the node 3, but the value 3. Then we call our self.next, and when we run into our self.next, what we pop off from the stack is exactly that value. And then we return the value. And the element that are now left on the stack is the node 7 is on the top, and below it, it's node 15. So next time a next is called, well, we run into this node's value, right? Because we put the root node's value in there. So we emit the 7. And now the 15 becomes the top of the stack. And when next is called for the third time, the 15 gets processed. It's a node. So we put the right subtree on the stack, the value 15, and the left subtree. Then we call ourselves, and it places the 9 on the top of the stack, the value 9, calls itself, and returns the value 9. So that's how that would work. So let me just delete the cheat method here. And let's just see if that works. Self.stack.pop. What am I doing wrong? Not enough values done, but expected 2 got 1. Are we only appending 1 value in any of those cases? Oh, here that is 1 too much. I think that is it. Yeah, there we go. So let's submit it to see if it passes all of the tests. And it sure does. And the awesome thing is now If you wanted to change this from an in-order traversal to a pre-order traversal, you only have to change the order of these 3 lines. Or if you wanted a post-order traversal, you would have to move this one to the top so that you emit a node only when you leave it. So yeah, so happy fun coding that one. And yeah, I hope you enjoyed it.